Question 1, Part A. Find the value of 1 over 7 plus 5 times 3, correct to three significant figures. We'll start by evaluating the fraction. Now, 1 over 7 plus 5 times 3 can be written as 1 divided by, open bracket, 7 plus 5 times 3, close bracket. Now, 7 plus 5 times 3 is 22. So the fraction is equivalent to 1 divided by 22, which is equal to 0.0454545 and so on. Now we want to round this decimal correct to three significant figures. Now the first significant figure, starting from the left-hand side, is the first non-zero digit, which is the 4. So the first three significant figures are the 4, the 5, and the 4. Now this 4 here needs to get rounded up to a 5 because the number next to it, so to the right of it, is 5. Now when it's 5 or more, we raise the score. So that 454 becomes 455. So 1 over 7 plus 5 times 3 is equal to 0.0455, correct to three significant figures. Question 1, Part B. Simplify 2 minus 3x in brackets minus 5 minus 4x in brackets. We'll start by expanding both sets of brackets. Now consider the first set of brackets around the 2 minus 3x. Now because it's the first set of brackets and there's nothing in front of the brackets, all we need to do is just remove the brackets. So we just have 2 minus 3x. However, the second set of brackets has a negative or a minus sign in front, and that needs to be taken into account when we're expanding or removing the brackets around 5 minus 4x. So the minus sign here is common to the 5 and the negative 4x. So if we're bringing the negative sign or the minus sign inside the brackets, we place it in front of the positive 5, and it becomes negative 5, and we also place it in front of the negative 4. So we have minus negative 4. So a minus minus or a minus negative turns into a positive. So the expanded expression becomes 2 minus 3x minus 5 plus 4x. The next step is to collect like terms. Now we have two constant terms that can be grouped together. So we have 2 minus 5, and we have two terms involving the variable x, minus 3x plus 4x. And I've written them in that order here. 2 minus 5 minus 3x plus 4x. Now 2 minus 5 is negative 3, and negative 3x plus 4x is positive or plus x. So the simplified expression can be written as negative 3 plus x, or we can write it the other way around. We can write it as x minus 3. Question 1, Part C. Write down the exact value of 135 degrees in radians. To convert from degrees to radians, starting with the degrees, we divide it by 180, but then we multiply that by pi. Think of pi as a pronumeral that represents 180. So dividing 135 by 180, we need to compensate for that by multiplying by a symbol that represents 180 degrees. So 135 over 180 times pi simplifies to 3/4 times pi, or 3 pi over 4 radians. Question 1, Part D. In the diagram, PQ is an arc of a circle with centre O. The radius OP equals 3 centimetres and the angle POQ is 5 pi over 6 radians. Find the length of the arc PQ. The arc length is given by the formula theta times r, where theta is the angle in the center of the sector in radians and r is the radius of the circle or the sector. In this case, theta is 5 pi over 6 radians and the radius r is 3 centimeters. So the arc length is equal to 5 pi over 6 times 3, which simplifies to 5 pi over 2 centimeters. Question 1, Part E. Using the table of standard integrals, find the integral of sec 3x tan 3x dx. And the excerpt from the table of standard integral reads, the integral of sec ax tan ax dx is equal to 1 over a times sec ax, where a is not equal to 0. The given rule is the integral of sec ax tan ax dx is equal to 1 over a times sec ax. In this case, a is equal to 3. So the integral of sec 3x tan 3x dx using the rule is equal to 1 over 3 times sec 3x plus the constant of integration c. Question 1, Part F. 45 balls, numbered 1 to 45, are placed in a barrel and one ball is drawn at random. What is the probability that the number on the ball drawn is even? There are 22 even numbers between 1 and 45. Hence, the probability of drawing an even number is 22 over 45, or approximately 48.9%. Question 1, Part G. By rationalising the denominator, express 8 over 3 minus the square root of 5 in the form a plus b times the square root of 5. Start by multiplying the numerator and the denominator by the conjugate of the denominator. The denominator is 3 minus root 5. Its conjugate is 3 plus root 5. And the reason why we do that is we take advantage of difference of two squares expansion. In other words, an expansion that results in a difference of two squares. We have an a minus b times a plus b case. And when we expand a minus b times a plus b, we get a squared minus b squared, which eliminates the term involving the surd in the denominator. So we're going to multiply 8 by 3 plus root 5 and 3 minus root 5 times 3 plus root 5. We get 8 times, open bracket, 3 plus root 5 close bracket, over 3 squared minus root 5 squared. That's the difference of two squares expansion that I was referring to earlier on. Now, expanding the brackets in the numerator, we get 24 plus 8 times root 5. And in the denominator, we get 9 minus 5. So simplifying the denominator, 9 minus 5 gives us 4. So the fraction becomes 24 plus 8 root 5 over 4, which we can simplify. 24 over 4 gives us 6, and 8 root 5 over 4 gives us 2 root 5. So 8 over 3 minus root 5, expressed with a rational denominator, or rationalized, is 6 plus 2 root 5. Question 2, Part A. The diagram shows a sketch of the curve y equals 6x squared minus x cubed. The curve cuts the x-axis at L and has a local maximum at M and a point of inflection at N. Part 1. Find the coordinates of L. The point L is an x-intercept, so that's a point where the graph crosses the x-axis. This implies that the y-coordinate of point L is 0. Hence, 6x squared minus x cubed equals 0 at point L. So we need to solve this equation for x. Also note that point L is to the right of the origin, so x must be greater than 0. Now factorising out x squared on the left-hand side of this equation, we get x squared outside of 6 minus x in brackets, and that equals 0. So by the null factor theorem, we have x is equal to 0 or 6. But x must be positive because point L is to the right of the origin, as I stated earlier. Therefore, the coordinates of point L are 6, 0. Part 2. Find the coordinates of M. Point M represents a stationary point. Hence, the value of the first derivative y dash is equal to 0. So differentiating y equals 6x squared minus x cubed with respect to x, we get y dash is equal to 12x minus 3x squared. And we want to solve the equation for x. 12x minus 3x squared is equal to 0. Now note that the value of x must be positive because the location of the stationary point is to the right of the origin. So we can simplify this equation by dividing all terms by 3x. And the equation simplifies to 4 minus x equals 0. And we get x is equal to 4. But we need the y-coordinate of point M. So noting that y is equal to 6x squared minus x cubed, and substituting 4 for x into that equation, at x equals 4, y is equal to 6 times 4 to the power of 2 minus 4 to the power of 3, which gives us 32. Therefore, the coordinates of point M are 4, 32. Part 3. Find the coordinates of N. Since N is a point of inflection which is given in the question, the value of the second derivative y double dash is equal to 0. Now from part 2, we found the first derivative, y dash is equal to 12x minus 3x squared. So to get the second derivative, we just have to differentiate the first derivative one more time with respect to x. So differentiating y dash, we get y double dash, or the second derivative, is equal to 12 minus 6x. Next, we solve the equation 12 minus 6x equals 0. And by inspection, we get x is equal to 2. Now at x equals 2, the y-coordinate we find by substituting 2 for x in the original equation. We get y is equal to 6 times 2 to the power of 2 minus 2 to the power of 3, which equals 16. Therefore, the coordinates of point N are 2, 16. Question 2, Part B. The graph of y equals f of x passes through the point 1, 4 and f dash of x equals 2x plus 7. Find f of x. If the derivative of f of x is f dash of x, then the antiderivative or the primitive of f dash of x is f of x. Hence, f of x is equal to the integral of 2x plus 7 with respect to x. So integrating 2x plus 7, we get x squared plus 7x plus the constant of integration c. Now it's given that the graph of y equals f of x passes through the point 1, 4. So f of 1 is equal to 4. So when we substitute 1 for x here and here, the value of f of 1 is equal to 4. So we can use that to find the value of the constant of integration c. Hence, 4 is equal to 1 squared plus 7 times 1 plus c. And solving this equation for c, we get c is equal to negative 4. Therefore, f of x is equal to x squared plus 7x minus 4. Question 2, Part C. Find a primitive of 2x over x squared plus 1. By inspection, the integrand is in the form f dash of x over f of x. The numerator is the derivative of the denominator. And when we have an integrand in this form, the primitive of 2x over x squared plus 1 is ln of the denominator. In other words, ln of x squared plus 1 plus the constant of integration c. Question 2, Part D. Consider the parabola with equation x squared equals 4 times y minus 1 in brackets. Part 1. Find the coordinates of the vertex of the parabola. The parabola with equation of the form x minus h in brackets to the power of 2 is equal to a times y minus k in brackets, where h, a and k are constants, has its vertex with coordinates h, k. Hence, x squared equals 4 times y minus 1 in brackets is a parabola whose vertex has coordinates 0, 1. Part 2. Find the coordinates of the focus of the parabola. Express the equation of the parabola in the form x squared equals 4a times y minus 1 in brackets, where a represents the focal length. That's the distance between the vertex and the focus. Now the original equation is x squared equals 4 times y minus 1 in brackets. So we equate the 4 with 4a. Now given that 4a is equivalent to 4 or equal to 4, 4a equals 4, which implies that a is equal to 1. That means the focal length is equal to 1, which means that the focus is 1 unit either above or below the vertex. Now the parabola is concave up. Hence, the focus is located 1 unit directly above the vertex. Now from part 1, we found that the vertex has coordinates 0, 1. So 1 unit directly above 0, 1 means the coordinates of the focus are at 0, 2. Question 3, Part A. Differentiate the following functions. Part 1. X squared plus 5 in brackets to the power of 3. By the chain rule, the derivative with respect to x of f of x to the power of n is equal to n times f of x to the power of n minus 1 multiplied by f dash of x. In other words, the derivative of the outer function, which is the power function, multiplied by the derivative of the inner function, which is f of x. In this case, our n is 3 and our f of x is x squared plus 5. So the derivative with respect to x of x squared plus 5 in brackets to the power of 3, using the rule, is equal to 3 times x squared plus 5 in brackets to the power of 2 multiplied by 2x, which is the derivative of x squared plus 5. Now this simplifies to 6x times x squared plus 5 in brackets to the power of 2. Part 2. Cos x over x. By the quotient rule, the derivative with respect to x of u over v, where u and v are both functions of x, is equal to u dash v minus uv dash over v squared. Hence, the derivative with respect to x of cos x over x, where u is equal to cos x and v is equal to x, is equal to negative sine x times x. So that's our u dash v minus cos x times 1. That's our u times v dash. And that's over v squared. So our v is x, so v squared is x squared. And this simplifies to negative x sine x minus cos x over x squared. Part 3. X squared times ln x. By the product rule, the derivative with respect to x of u times v, where u and v are functions of x, is equal to u dash v plus uv dash. Hence, the derivative with respect to x of x squared times ln x, where u is equal to x squared and v is equal to ln x, is equal to 2x times ln x. So that's our u dash times v plus x squared times 1 over x. That's our u times v dash. Now x squared times 1 over x simplifies to x. So the derivative is equal to 2x times ln x plus x. And if we wanted to, we could factorize out x from this term, and that equals x times, open bracket, 2 times ln x plus 1, close bracket. Question 3, Part B. Let A and B be the points 0, 1 and 2, 3 respectively. Part 1. Find the coordinates of the midpoint of AB. To help with visualization, I've sketched a number plane and shown the 2 points A and B roughly located on this number plane. So here is point A with coordinates 0, 1, so it happens to be a y-intercept of the line through AB. And here is point B with coordinates 2, 3. I've let capital M represent the midpoint of AB. And I'm going to show that also by drawing these dashes here as well, so to indicate that AM is equal to MB. Now to find the coordinates of the point capital M, which is the midpoint of AB, we find the average of the x coordinates of A and B, and then the average of the y coordinates of A and B. Now the average of the x coordinates, 0 plus 2 over 2 gives us 1, and the average of the y coordinates, 1 plus 3 over 2 gives us 2. So the midpoint of AB has coordinates 1, 2. Part 2. Find the slope of the line AB. The slope or gradient of the line through points A and B is given by the formula change in y divided by change in x, otherwise known as rise over run. Now from left to right, the change in y, or the vertical change, going from 1 to 3 is given by 3 minus 1 in brackets, and the change in x, starting from 0 ending up at 2, the change in x is the difference between 2 and 0, so 2 minus 0, and that gives us 2. So 3 minus 1 in brackets divided by 2 minus 0 in brackets gives us 1. Therefore, the gradient of AB is 1. Part 3. Find the equation of the perpendicular bisector of AB. I've indicated the perpendicular bisector on the diagram. It's a line that passes through the midpoint M of AB, and that's why it's called a bisector, and it's perpendicular because it's at an angle of 90 degrees to the line that passes through AB. Now firstly we need to find the gradient of the perpendicular bisector, and that's given by -1 divided by the gradient of AB, which we found in part 2. And that comes from the formula M1 times M2 equals -1, where M1 and M2 are the gradients of the two lines that are 90 degrees to each other. So -1 divided by 1 gives us -1. Next we need to consider the point that this line passes through. So the perpendicular bisector passes through the midpoint, which has coordinates 1, 2. So using the point gradient formula, that's y minus y1 is equal to m times x minus x1 in brackets. We have y minus 2 is equal to -1 times x minus 1 in brackets. Expanding the brackets, we get y minus 2 is equal to -x plus 1. And then rearranging this equation into gradient intercept form, we get y is equal to -x plus 3. Part 4. The point P lies on the line y equals 2x minus 9 and is equidistant from A and B. Find the coordinates of P. Since point P lies on the line y equals 2x minus 9, this implies that P has coordinates x, 2x minus 9. Now it's given that point P is equidistant from points A and B. That means the distance from point A to P is equal to the distance from point B to P. So this means that PA is equal to PB. Now thinking ahead, we will need to use the distance formula, and that involves using a surd or a square root. But in order to avoid using the surd or the square root, we could make it a little easier to apply the distance formula if we square PA and PB. So if PA is equal to PB and they're both positive values, we can square both sides of the equation, maintaining its integrity. So PA squared is equal to PB squared. So using the distance formula, or the square of the distance formula, so we don't have to use the surd or the square root, we have x minus 0 in brackets squared plus 2x minus 9 minus 1 in brackets squared is equal to x minus 2 in brackets squared plus 2x minus 9 minus 3 in brackets squared. Now x minus 0 is x, so x minus 0 in brackets squared simplifies to x squared. 2x minus 9 minus 1 simplifies to 2x minus 10, so we have 2x minus 10 in brackets squared is equal to x minus 2 in brackets squared plus 2x minus 12 in brackets squared. Now expanding the brackets here, here and here, so using perfect square expansion, we get x squared plus 4x squared minus 40x plus 100 is equal to x squared minus 4x plus 4 plus 4x squared minus 48x plus 144. Now we have some cancellation. We can cancel the x squared here and here. We can also cancel the 4x squared here and here. So that leaves us negative 40x plus 100 is equal to negative 52x plus 148 after we collect like terms. So we have a plus 4 and a plus 144, and that's why we get the plus 148 there. Also, we get the negative 4x minus 48x, which is why we get the negative 52x here. So rearranging this equation, again collecting like terms further, we move the x's over to the left-hand side and the constant terms over to the right-hand side. We get 12x is equal to 48, which means x is equal to 4, and that's the x coordinate of point P, but we also need the y coordinate. Now, it's given that y is equal to 2x minus 9, and that's the y coordinate of point P. So given that x is equal to 4, which we just found, y is equal to 2 times 4 minus 9, which equals negative 1. Therefore, point P has coordinates 4, negative 1. Question 4, Part A. The table shows the values of a function f of x for 5 values of x. Use Simpson's rule with these 5 values to estimate the integral of f of x dx from x equals 1 to x equals 3. 5 function values provided implies 2 applications of Simpson's rule. Now the width of one strip or one interval, h, is 0.5, and we find that by finding the difference between any 2 successive x values. Recall the x values in the top row of the table start from 1 and go up in steps of 0.5, and that's why h is 0.5. I'm going to use the extended form of Simpson's rule rather than doing 2 explicit applications of Simpson's rule. So the integral of f of x dx from x equals 1 to x equals 3 is approximately equal to h over 3, so that's 0.5 over 3 times open bracket 5 plus 4 times 1 plus 2 times negative 2 plus 4 times 3 plus 7 close bracket. So this integral is approximately equal to 4. Question 4, Part B, Part 1. Sketch the graph of y equals x squared minus 6 and label all intercepts with the axes. The graph of the polynomial function y equals x squared minus 6 is a concave up parabola. Now we know it's a parabola because the highest power of x is 2, and we know it's concave up because the coefficient or the number that multiplies x squared is positive. Even though it's not shown, it's positive 1. Now to find the x-intercepts, we let y equal 0, and we do that because the y-coordinate of the x-intercepts is 0. Then we solve the equation 0 equals x squared minus 6. So if we rearrange the equation to make x squared the subject, we get x squared is equal to 6. Taking the square root of both sides of the equation, we get x is equal to plus or minus the square root of 6. Alternatively, we can factorize x squared minus 6 as a difference of two squares, let y equal 0, and then apply the null factor theorem to find the x-intercepts. So y is equal to x minus root 6 in brackets times x plus root 6 in brackets, and by the null factor theorem, we get x-intercepts negative root 6 and root 6. Now to find the y-intercept, we let x equal 0 and then evaluate x squared minus 6. And of course we get negative 6. So the y-intercept is negative 6. So the graph is a concave up parabola with x-intercepts negative root 6 and root 6, and the y-intercept of negative 6 centered on the y-axis. So here is a sketch of the parabola y equals x squared minus 6. Now the vertex or the turning point of the parabola sits on the y-axis, which corresponds to the y-intercept of negative 6. So here is one x-intercept at negative root 6 and the other x-intercept at root 6. Now to get the shape as accurately as possible, I've located some other convenient points and then I've sketched the curve as best as possible going through all those points. Part 2. On the same set of axes, carefully sketch the graph of y equals the absolute value of x. The graph of the function y equals the absolute value of x is a V shape that points upward. The vertex of the V is on the origin, and we have a positive branch and a negative branch that are straight lines. Now, the positive branch passes through the point 3, 3, and the negative branch passes through the point negative 3, 3. Part 3. Find the x-coordinates of the 2 points where the graphs intersect. Referring to the graphs drawn in parts 1 and 2, the graph of y equals x squared minus 6 intersects with the graph of y equals the absolute value of x at these 2 points. And the x-coordinates of these 2 points are negative 3 and 3. So I've stated the answer here. The graph of y equals x squared minus 6 intersects with the graph of y equals the absolute value of x, where x is equal to negative 3 and where x is equal to 3. Part 4. Hence solve the inequality x squared minus 6 less than or equal to the absolute value of x. From the graphs drawn in parts 1 and 2, and taking into account the x-coordinates of the points of intersection of both graphs that we stated in part 3, that is at x equals negative 3 and at x equals 3, the inequality x squared minus 6 less than or equal to the absolute value of x refers to the part of the graph where the parabola x squared minus 6 is on or below the graph of y equals the absolute value of x. And that occurs between x equals negative 3 and at x equals 3, inclusive of the endpoints. So the solution to the inequality x squared minus 6 less than or equal to the absolute value of 6 is x greater than or equal to negative 3 and less than or equal to 3. Question 4, Part C. The diagram shows the graphs of the functions y equals cos x and y equals sine 2x between x equals 0 and x equals pi over 2. The two graphs intersect at x equals pi over 6 and x equals pi over 2. Calculate the area of the shaded region. The area of the shaded region is equal to the area under the curve y equals sine 2x in the interval x greater than or equal to 0 and less than or equal to pi over 6, plus the area under the curve y equals cos x in the interval x greater than or equal to pi over 6 and less than or equal to pi over 2. Expressing that as a sum of two integrals, we have the integral of sine 2x dx from x equals 0 to x equals pi over 6, plus the integral of cos x dx from x equals pi over 6 to x equals pi over 2. Performing the integration, we get negative cos 2x over 2 from x equals 0 to x equals pi over 6, plus sine x from x equals pi over 6 to x equals pi over 2. Applying the limits of integration, we get negative cos of pi over 3 all over 2 minus negative cos 0 over 2 in brackets, plus sine pi over 2 minus sine pi over 6 in brackets. Now, negative cos pi over 3 all over 2 is negative 1 over 4. We have a double negative, so that turns it into a positive. So minus negative cos 0 over 2 is positive 1 over 2, or plus half, plus sine pi over 2, which is 1, minus sine pi over 6, which is 1 over 2. So we have negative 1 over 4 plus 1 over 2 plus 1 minus 1 over 2, and that evaluates to 3 over 4 square units. Question 5, Part A. Evaluate the integral of e to the power of negative x dx from x equals 0 to x equals ln of 7. The primitive or integral of e to the power of negative x is e to the power of negative x divided by the derivative of the index, which in this case is negative 1. So the integral of e to the power of negative x dx from x equals 0 to x equals ln of 7 is equal to e to the power of negative x divided by negative 1 from x equals 0 to x equals ln of 7. And that can be written as negative e to the power of negative x from x equals 0 to x equals ln of 7. Applying the limits of integration, we get negative e to the power of negative ln of 7 minus negative e to the power of negative 0. Now, the double negative here becomes a positive here, and e to the power of negative 0 is equal to e to the power of 0, which is equal to 1. And it's important to note that negative ln of 7 can be written as ln of 1 over 7. So negative e to the power of negative ln of 7 minus negative e to the power of negative 0 is equal to negative e to the power of ln of 1 over 7 plus 1. Now the e and the ln functions cancel, and we're left with negative 1 over 7 plus 1, and that simplifies to 6 over 7. Question 5, Part B. In the diagram, ABCD is a square. The points P, Q and R lie on AB, BC and CD respectively, such that AP equals BQ equals CR. Part 1. Prove that triangles PBQ and QCR are congruent. Firstly, we have angle PBQ equals angle QCR, which equals 90 degrees. So here's angle PBQ, here's angle QCR. And the reason is interior angles of square ABCD are 90 degrees. Next, we have BQ equals CR, which equals PA. So here's BQ equal to CR, which is equal to PA. And that's already given. Now, AB is equal to BC, so here's side AB, and that's equal to side BC because they are sides of square ABCD and they are equal. Hence, BP plus PA, so that's BP plus PA, is equal to BQ plus QC. And since BQ is equal to PA, or PA is equal to BQ, this implies that BP is equal to QC. Therefore, triangle PBQ is congruent to triangle QCR by the side angle side test. Part 2. Prove that angle PQR is a right angle. Angle BQP equals angle CRQ, which equals alpha. And the reason is corresponding angles of congruent triangles PBQ and QCR proven in part 1. Also by the same reason, angle BPQ equals angle CQR, which equals beta. Now in either triangle PBQ or QCR, alpha plus beta plus 90 degrees is equal to 180 degrees because it's the angle sum of a triangle. So if we subtract 90 degrees from either side of that equation, so alpha plus beta plus 90 equals 180, take away 90 from both sides, this implies that alpha plus beta is equal to 90 degrees. Now on line BC, we have this angle here, so angle BQP plus angle PQR plus angle CQR is equal to 180 degrees because we have angles on a line and adjacent angles on a line are supplementary, which means they add up to 180 degrees. Now we've previously shown that alpha plus beta is equal to 90 degrees, which means the remaining angle must be 90 degrees so that they all add up to 180 degrees. And here is the proof. So I'll just go through it again. Angle BQP equals angle CRQ, which equals alpha. The reason is corresponding angles of congruent triangles PBQ and QCR, proven in part 1. Also by the same reason, angle BPQ equals angle CQR, which equals beta. Now in either triangle PBQ or QCR, alpha plus beta is equal to 90 degrees because we have the angle sum of a triangle and that's equal to 180 degrees. And on line BC, angle BQP plus angle PQR plus angle CQR is equal to 180 degrees. That's because angles on a line add up to 180 degrees. So going back to this equation here, angle BQP is alpha, angle CQR is beta. So alpha plus angle PQR plus beta is equal to 180 degrees, but alpha plus beta is 90 degrees, and I've shown that here. So 90 degrees plus angle PQR is equal to 180 degrees. Therefore, angle PQR is equal to 90 degrees as required. Question 5, Part C. The rate of inflation measures the rate of change in prices. Between January 1996 and December 1996, prices were rising, but the rate of inflation was falling. Draw a graph of prices as a function of time that fits this description. Prices are rising over time, but the rate at which prices are rising is falling. So the curve used to model this situation is a curve that's increasing but at a decreasing rate. Now if P represents prices and T represents time, the first derivative dP dt is greater than 0 or positive, but the second derivative d squared P over dt squared is less than 0 or negative. So it's a curve that's increasing but at a decreasing rate. From the point of view of concavity, it's a curve that's concave down from January 1996 to December 1996. Question 5, Part D. A ball is dropped from a height of 2 meters onto a hard floor and bounces. After each bounce, the maximum height reached by the ball is 75% of the previous maximum height. Thus, after it first hits the floor, it reaches a height of 1.5 meters before falling again, and after the second bounce, it reaches a height of 1.125 meters before falling again. Part 1. What is the maximum height reached after the third bounce? We can model this situation using a recurrence relation. So that's applying the same operation to a previous result to get the current result. So let Hn equal the maximum height of the ball reached after the nth bounce. So before the ball bounces, initially h0 is equal to 2 meters above the ground. So h1, which is the maximum height of the ball reached after the first bounce, is equal to h0 times 0.75 or 75%. Now h0 is equal to 2, so h1 is equal to 2 times 0.75, which equals 1.5. So to get h2, we repeat the same operation. We take the previous result, so h1, which is 1.5, and we multiply that by 75% or 0.75. So 1.5 times 0.75 is equal to 1.125. And to get h3, we take h2, we multiply that by 75% or 0.75 again. So 1.125 times 0.75 is equal to 0.84375. So interpreting that result, the maximum height reached after the third bounce is 0.84375 meters or 84.375 centimeters. Part 2. What kind of sequence is formed by the successive maximum heights? The sequence is h0, h1, h2, h3, and so on. Now from part 1, h0 is 2, h1 is 1.5, h2 is 1.125, h3 is 0.84375. To get the next term, we multiply the previous term by 75% or 0.75. So this is a geometric sequence with the first term a equal to 2 and a common ratio r equal to 0.75. Part 3. What is the total distance travelled by the ball from the time it was first dropped until it eventually comes to rest on the floor? From parts 1 and 2, we can model the total distance travelled by the ball using this particular series. Now the ball starts off at a maximum height of 2 meters above the ground. It then falls 2 meters to the ground due to gravity, and it bounces back up to a maximum height of 1.5 meters. And that's why I've used a down arrow here and an up arrow here so we can visualize what is going on. Now the ball then drops 1.5 meters, hits the ground, and then bounces back up to a new maximum height of 1.125 meters. It then falls 1.125 meters, hits the ground, and then bounces back up to a new maximum height of 0.84375 meters, and the pattern continues. Now, ignoring the first term, what you'll notice is that the sequence that we had in part 2, I'll just go back to that. Ignoring the 2, each subsequent term is doubled because the ball has to rise up to a maximum height and then fall back to the ground that same distance that's equal to the maximum height. So we can rewrite this series in this way. So taking out the first term of 2, noting that every subsequent term is doubled, we can write it as 2 plus 2 times, open bracket, 1.5 plus 1.125 plus 0.84375, and so on, close bracket. Now what we have in the brackets here is a geometric series, first term 1.5, and a common ratio that's less than 1 and greater than -1, or the absolute value of the common ratio is less than 1. So we can evaluate what's in the brackets here using the limiting sum of a geometric series formula, a over 1 minus r. So we have 2 plus 2 times the limiting sum of this geometric series. So that's 1.5 over 1 minus 0.75. So 2 plus 2 times 1.5 over 1 minus 0.75 evaluates to 14. Therefore, the total distance travelled by the ball is 14 meters. Question 6, Part A. A wire of length 5 meters is to be bent to form the hypotenuse and base of a right-angled triangle PQR as shown in the diagram. Let the length of the base QR be x meters. Part 1. What is the length of the hypotenuse PQ in terms of x? The hypotenuse PQ plus the base QR is equal to 5 meters. Now, the length of QR is x meters, so we can form this equation. PQ plus x is equal to 5. Rearranging this equation to make PQ the subject, we get PQ is equal to 5 minus x meters. Part 2. Show that the area of the triangle PQR is half x times the square root of 25 minus 10x square meters. The area of a triangle is given by the formula half times the base times the perpendicular height. Now in triangle PQR, the base is QR and the perpendicular height is PR. Now the length of QR is x meters, but we need to find the height PR in terms of x. Now from part 1, we found the length of the hypotenuse, which is 5 minus x meters. And because we have a right-angled triangle, we can find PR in terms of x using Pythagoras' theorem. So PR squared is equal to PQ squared minus QR squared. So PR squared is equal to 5 minus x in brackets squared minus x squared. Now we have a perfect square here, which we can expand. So PR squared is equal to 25 minus 10x plus x squared minus x squared. Now the x squareds will cancel to 0. So we have PR squared is equal to 25 minus 10x. But we don't want PR squared, we want PR. So in order to obtain PR, we need to take the square root of 25 minus 10x. So PR is equal to the square root of 25 minus 10x meters. So the area of triangle PQR is equal to half times QR times PR, so that's half times base times perpendicular height, and that's equal to half times x times the square root of 25 minus 10x. So we get A is equal to half x times the square root of 25 minus 10x square meters, where A is equal to the area of triangle PQR as required. Part 3. What is the maximum possible area of the triangle? Part 3 is asking for the maximum possible area of triangle PQR. Now from part 2, we know that the area A is equal to half x times the square root of 25 minus 10x square meters. So we want to find a value of x which gives us the maximum possible value of A. Now this will involve the use of differential calculus. We'll need to differentiate A with respect to x, solve the equation A dash equals 0, find the value of x that gives us A dash equals 0, and then test to see if that value of x corresponds to the maximum possible value of A. Now in order to differentiate A with respect to x, we need to express A in terms of x using index notation rather than surd notation. So A is equal to half x times 25 minus 10x in brackets to the power of 1 over 2. Now we have a product of two functions of x, so to differentiate A with respect to x we can use the product rule. So the first derivative A dash is equal to u dash v plus uv dash, where u is equal to half x, v is equal to 25 minus 10x in brackets to the power of 1 over 2. Now u dash is equal to half, and to find v dash we need to use the chain rule. And we get half times 25 minus 10x in brackets to the power of negative 1 over 2 times negative 10, which simplifies to negative 5 times open bracket 25 minus 10x close bracket to the power of negative 1 over 2. So putting that all together, using the product rule, we get A dash is equal to half times 25 minus 10x in brackets to the power of 1 over 2 minus 5x over 2 times open bracket 25 minus 10x close bracket to the power of negative 1 over 2. So writing A dash Using surd notation, we get a dash is equal to the square root of 25 minus 10x over 2 minus 5x over 2 times the square root of 25 minus 10x. Now we can combine these two fractions together if we can find a common denominator. So if we take the first fraction and multiply the numerator and the denominator by the denominator of the second fraction, we can get two fractions with the same denominators, which means we can then combine the two fractions. So a dash is equal to 25 minus 10x over 2 times the square root of 25 minus 10x minus 5x over 2 times the square root of 25 minus 10x. Now that the two fractions have a common denominator, we can combine the numerators together to form a single fraction. So 25 minus 10x minus 5x, we have negative 10x minus 5x gives us negative 15x. So a dash is equal to 25 minus 15x over 2 times the square root of 25 minus 10x. Next we solve the equation a dash equals 0. And because we're dealing with a fraction, the only way a fraction can equal 0 is if the numerator equals 0. And in this case, the numerator is 25 minus 15x, and we're solving 25 minus 15x equals 0. Rearranging the equation, we get 15x is equal to 25. Dividing both sides of the equation by 15 to isolate x, we get x is equal to 5 over 3 meters. Next, we need to test if x equals 5 over 3 corresponds to the maximum area of triangle PQR. And we can use a table of gradients to check this. So here is my table of gradients. Now when x is equal to 5 over 3, the value of a dash is 0. And I've chosen two values on either side of x equals 5 over 3. So I've chosen x equals 1.5 to the left of x equals 5 over 3, and I've chosen x equals 2, which is a value to the right of x equals 5 over 3. Now when x is equal to 1.5, the value of a dash is 0.395, which is positive, so that's a positive gradient to the left of x equals 5 over 3. When x is equal to 5 over 3, of course we get a dash of 0, so that's a horizontal gradient. And when x is equal to 2, the value of a dash is negative 1.118 and so on, and that gives us a negative gradient to the right of x equals 5 over 3. So from the table of gradients, x equals 5 over 3 corresponds to the maximum area of triangle PQR. Now from part 2, we have area A is equal to half times x times the square root of 25 minus 10x square meters. So when x is equal to 5 over 3, substituting this value for x here and here, we get A is equal to 2.4056 and so on. I haven't written the full decimal on the calculator screen, so I'm going to round the answer correct to 2 decimal places. Therefore, the maximum possible area is 2.41 square meters, correct to 2 decimal places, or 25 root 3 over 18 square meters in exact form. Question 6, Part B. A logo is made of 20 squares with a common corner, as shown in the diagram. The odd-numbered stripes between successive squares are shaded in the diagram. The shaded stripes are painted in gold paint, which costs $9 per square centimetre. The side length of the nth square is 2n plus 4 centimetres. The nth stripe lies between the nth square and the n plus 1th square. Part 1. Show that the area of the nth stripe is 8n plus 20 square centimetres. The nth stripe lies between the nth square and the n plus 1 square, and the n plus 1 square is bigger than the nth square. So the area of the nth stripe is the difference between the n plus 1 square and the nth square. And that's equal to the area of the n plus 1 square minus the area of the nth square. Now the side length of the nth square is given as 2n plus 4 centimetres. So to find the area of the nth square, we square 2n plus 4. So we get 2n plus 4 in brackets to the power of 2 square centimetres. Now to find the side length of the n plus 1 square, we substitute n plus 1 for n for the side length of the nth square, since we've increased n by 1. So the side length of the n plus 1 square is 2 times n plus 1 in brackets plus 4 centimetres. And that simplifies to 2n plus 6 when we expand the brackets here and collect like terms. Hence the area of the n plus 1 square is 2n plus 6 in brackets to the power of 2 square centimetres. So to find the area of the nth stripe, we subtract 2n plus 4 in brackets squared from 2n plus 6 in brackets squared. So area of the nth stripe is equal to 2n plus 6 in brackets squared minus 2n plus 4 in brackets squared. Expanding the brackets using perfect square expansion, that equals 4n squared plus 24n plus 36 minus, open bracket, 4n squared plus 16n plus 16, close brackets. So expanding the brackets here, we get 4n squared plus 24n plus 36 minus 4n squared minus 16n minus 16. Now the 4n squared here will cancel with the negative 4n squared here, and we can collect some like terms. So we get 24n minus 16n gives us 8n, and 36 minus 16 gives us positive 20. Therefore the area of the nth stripe is 8n plus 20 square centimetres as required. Part 2. Hence find the areas of the first and last stripes. Given that there are 20 squares in the pattern, this means there are 19 stripes in between those 20 squares. So the value of n that corresponds to the first stripe is 1, and the value of n that corresponds to the last stripe is 19. Now from part 1, the expression that gives us the area of the nth stripe is 8n plus 20 square centimetres. So to find the area of the first stripe, we substitute n equals 1 into this expression. So we get area A1 is equal to 8 times 1 plus 20, which equals 28 square centimetres. To find the area of the last stripe, we substitute n equals 19 into this expression. So we get area A19 is equal to 8 times 19 plus 20, which equals 172 square centimetres. Part 3. Hence find the total cost of the gold paint for the logo. Every odd stripe in the logo will be painted in gold, and the total area of every odd stripe is the sum of an arithmetic series of 10 terms. That is A1 plus A3 plus A5 plus plus A19. With the first term equal to 28, the last term equal to 172, and we found those in part 2, and n is equal to 10, and that represents the number of terms in this series. So the total area is given by the formula n over 2 times a plus l in brackets, where n is the number of terms in the series, and that's 10. A represents the first term of the series, which is 28, and L represents the last term of the series, which is 172. So the total area is equal to 10 over 2 times 28 plus 172 in brackets, and that evaluates to 1,000 square centimetres. So to find the total cost of paint, we take the area that we just found, which is 1,000 square centimetres, and then multiply it by the cost per square centimetre, which is $9 per square centimetre. So the total cost of paint is equal to 1,000 times 9, which is equal to $9,000. Question 7, Part A. By expressing sec theta and tan theta in terms of sine theta and cos theta, show that sec squared theta minus tan squared theta equals 1. Starting from the left-hand side, we have left-hand side is equal to sec squared theta minus tan squared theta. Now, in terms of sine theta and cos theta, sec squared theta is equivalent to 1 over cos squared theta, and tan squared theta is equivalent to sine squared theta over cos squared theta. So the left-hand side is equal to 1 over cos squared theta minus sine squared theta over cos squared theta. So we have the difference of two fractions and the denominators are identical, so we can combine the numerators by subtraction. So we have left-hand side is equal to 1 minus sine squared theta over cos squared theta. Now recall that sine squared theta plus cos squared theta is equal to 1. And if we rearrange that identity to make cos squared theta the subject, we get cos squared theta is equal to 1 minus sine squared theta. So the numerator, 1 minus sine squared theta, is equivalent to cos squared theta. So the fraction simplifies to cos squared theta over cos squared theta, which is equal to 1. And that's equal to the right-hand side. Therefore, sec squared theta minus tan squared theta is equal to 1 as required. Question 7, Part B. The diagram shows part of the graph of the function y equals tan 2x. The shaded region is bounded by the curve, the x-axis, and the line x equals pi over 6. The region is rotated about the x-axis to form a solid. Part 1. Show that the volume of the solid is given by v equals pi times the integral of sec squared 2x minus 1 dx from x equals 0 to x equals pi over 6. You may use the result of Part A. Since the volume of the solid is generated by rotating the curve about the x-axis, the volume V is given by the expression pi times the integral of y squared dx from x equals a to x equals b. Now in this case, y is equal to tan 2x, so y squared is equal to tan squared 2x. So this is the integrand. A is 0 and b is pi over 6. So the volume V is given by pi times the integral of tan squared 2x dx from x equals 0 to x equals pi over 6. Now from Part A, we found that sec squared theta minus tan squared theta is equal to 1, and this is what was proven. Rearranging this identity to make tan squared theta the subject, we get tan squared theta is equal to sec squared theta minus 1. Now in this case, theta is equal to 2x. Hence, tan squared 2x is equal to sec squared 2x minus 1. Now the integral can be written in terms of sec squared 2x. Therefore, the volume V is equal to pi times the integral of sec squared 2x minus 1 dx from x equals 0 to x equals pi over 6. Part 2. Find the exact volume of the solid. From Part 1, the volume V is given by the expression V equals pi times the integral of sec squared 2x minus 1 dx from x equals 0 to x equals pi over 6. The integral of sec squared 2x is tan 2x divided by 2, or half times tan 2x, and the integral of 1 is x. So V is equal to pi times, open bracket, half times tan 2x minus x, close bracket, from x equals 0 to x equals pi over 6. Applying the limits of integration, we get V is equal to pi times, open bracket, half times tan pi over 3 minus pi over 6 minus 0, close bracket. Now tan pi over 3 is an exact trigonometric ratio, which is equivalent to root 3. So we get V is equal to pi times, open bracket, half times root 3 minus pi over 6, close bracket. Now factorising out 1 over 6 from both of these terms, we get V is equal to pi over 6 times open bracket, 3 times root 3 minus pi, close bracket. Therefore, the volume of the solid is pi over 6 times 3 root 3 minus pi in brackets cubic units. Question 7, Part C. A ball is dropped into a long vertical tube filled with honey. The rate at which the ball decelerates is proportional to its velocity. Thus, dv dt equals negative kv, where v is the velocity in centimeters per second, t is the time in seconds, and k is a constant. When the ball first enters the honey, at t equals 0, v equals 100. When t equals 0.25, v equals 85. Part 1. Show that v equals c times e to the power of negative kt satisfies the equation dv dt equals negative kv. v is equal to c times e to the power of negative kt. Differentiating v with respect to t, we get dv dt is equal to c times e to the power of negative kt, which is the original function, multiplied by the derivative of the index of e. Now the index of e is negative kt, and differentiating negative kt with respect to t, we get negative k. So what we've done in effect is to apply the chain rule. So dv dt is equal to c times e to the power of negative kt times negative k. Now c times e to the power of negative kt is equivalent to v. So we can replace this part of the expression with v. So dv dt is equal to v times negative k, which is equal to negative kv. Therefore, v equals c times e to the power of negative kt satisfies the equation dv dt is equal to negative kv. Part 2. Find the value of the constant c. One of the boundary conditions given is that when t is equal to 0, v is equal to 100. Now v is equal to c times e to the power of negative kt. So substituting 0 for t and 100 for v, we can form this equation. 100 is equal to c times e to the power of negative k times 0. Now negative k times 0 is 0, so the equation becomes 100 is equal to c times e to the power of 0, and e to the power of 0 is equal to 1. So 100 is equal to c, therefore c is equal to 100. Part 3. Find the value of the constant k. In order to find k, we need to apply the second boundary condition. It is given that when t is equal to 0.25, v is equal to 85. Now in part 2, we found the value of c, which was 100. So the equation for v is v equals 100 times e to the power of negative kt. So substituting 85 for v here and 0.25 for t here, we can form this equation and we can solve it for k. So we have 85 is equal to 100 times e to the power of negative 0.25k. Dividing both sides of the equation by 100, we get 0.85 is equal to e to the power of negative 0.25k. Because we're dealing with base e, we take the log base e of both sides of the equation in order to isolate k. So we have ln of 0.85 is equal to ln of e to the power of negative 0.25k. Now the ln and the e cancel. So we have ln of 0.85 is equal to negative 0.25k. So to isolate k, we divide both sides of the equation by negative 0.25. So we get k is equal to ln of 0.85 divided by negative 0.25, and that's equivalent to multiplying ln of 0.85 by negative 4. So k is equal to negative 4 times ln of 0.85. And I've expressed this answer here. Therefore, k equals negative 4 times ln of 0.85. Part 4. Find the velocity when t equals 2. We want to find the value of v when t is equal to 2. So substituting 2 for t in the velocity equation, we get v of 2 is equal to 100 times e to the power of negative 2k. And in part 3, we found the value of k, which was negative 4 times ln of 0.85. So v of 2 is equal to 100 times e to the power of negative 2 times negative 4 times ln of 0.85, which is equal to 27.249, correct to 3 decimal places. Therefore, the velocity of the ball is 27.249 centimeters per second at time t equals 2, correct to 3 decimal places. Question 8, Part A. In the isosceles triangle ABC, angle ABC equals angle ACB equals alpha. The points D and E lie on BC and AC so that AD equals AE as shown in the diagram. Let angle BAD equal beta. Part 1. Explain why angle ADC equals alpha plus beta. In triangle ABD, angle ADC is equal to angle ABD plus angle BAD. And the reason is exterior angle ADC is equal to the sum of the opposite interior angles in triangle ABD. Now angle ABD is equal to angle ABC, which is equal to alpha, and angle BAD equals beta. And that was given in the question. Therefore, angle ADC is equal to alpha plus beta. Part 2. Find angle DAC in terms of alpha and beta. In triangle ABC, angle ABC plus angle BCA plus angle BAD plus angle DAC is equal to 180 degrees. And the reason is angle sum of a triangle is equal to 180 degrees. Now angle ABC is equal to alpha, angle BCA is equal to alpha, and angle BAD is equal to beta. So we have alpha plus beta plus angle DAC is equal to 180 degrees. And collecting the like terms, we get 2 alpha plus beta plus angle DAC is equal to 180 degrees. Rearranging this equation to isolate angle DAC, we get angle DAC is equal to 180 degrees minus 2 alpha minus beta, or angle DAC is equal to pi minus 2 alpha minus beta in radians. Part 3. Hence or otherwise, find angle EDC in terms of beta. In triangle ADE, AD is equal to AE, and that's given in the question. This makes triangle ADE isosceles. This means the base angles are equal. So angle ADE is equal to angle AED. Now in part 2, we found the size of angle DAC, which is the same as angle DAE, since E lies on AC, and that's 180 degrees minus 2 alpha minus beta. And if we take all three angles in triangle ADE, add them together, we'll get 180 degrees, because that's the angle sum of a triangle. So going through the proof, in triangle ADE, AD is equal to AE, and that's given in the question, hence triangle ADE is isosceles. Angle ADE is equal to angle AED, because they're the base angles of isosceles triangle ADE. Now angle DAC is equal to angle DAE, which is equal to 180 degrees minus 2 alpha minus beta, and that was previously proven in part 2. And if we add the two base angles and the apex angle together, so angle ADE plus angle AED plus angle DAE, we get 180 degrees, because that's the angle sum of a triangle. Now since angle ADE is equal to angle AED, we can write this equation here in terms of angle ADE. So 2 times angle ADE plus 180 degrees minus 2 alpha minus beta is equal to 180 degrees. Subtracting 180 degrees from both sides of the equation, we get 2 times angle ADE minus 2 alpha minus beta is equal to 0 degrees. So moving the negative 2 alpha minus beta on the left-hand side over to the right-hand side, the equation becomes 2 times angle ADE is equal to 2 alpha plus beta. And dividing both sides of the equation by 2, we get angle ADE is equal to alpha plus beta over 2. Angle ADE plus angle EDC is equal to angle ADC. And that's because they are adjacent angles. So going back to the diagram, so this angle here, angle ADE plus angle EDC is equal to angle ADC. So angle ADE is equal to alpha plus beta over 2 plus angle EDC is equal to alpha plus beta. Now in part 1, angle ADC is equal to alpha plus beta, and we're asked to explain why. So we can form this equation. Alpha plus beta over 2 plus angle EDC is equal to alpha plus beta. And we will solve for angle EDC. So subtracting alpha from both sides of the equation, we get beta over 2 plus angle EDC is equal to beta. And subtracting beta over 2 from both sides of the equation, we get angle EDC is equal to beta minus beta over 2, or beta minus half beta. And that simplifies to beta over 2. Therefore, angle EDC is equal to beta over 2 in terms of beta. Question 8, Part B. A particle is moving along the x-axis. Its position at time t is given by x equals t plus sine t. Part 1. At what times during the period t greater than 0 and less than 3 pi is the particle stationary? The displacement equation is x equals t plus sine t. Now, velocity is the rate of change of displacement with respect to time. So to get the velocity equation, we find the derivative of x with respect to t, so dx dt. So differentiating t plus sine t with respect to t, we get the velocity v is equal to 1 plus cos t. So we need to solve for t the equation v equals 0. So when the velocity is equal to 0, the particle is stationary. So 1 plus cos t is equal to 0. Rearranging the equation to isolate cos t, we get cos t is equal to negative 1. And solving this equation with respect to t using inverse cos of negative 1, we get t is equal to pi, 3 pi, 5 pi, and so on. But t has to be a value greater than 0 and less than 3 pi. So t equals 3 pi is not a valid solution. Therefore, the only valid solution is the particle is stationary at time t equals pi. Part 2. At what times during the period t greater than 0 and less than 3 pi is the acceleration equal to 0? The velocity equation is v equals 1 plus cos t, which we found in part 1. Now the acceleration a is the rate of change of velocity with respect to time. In other words, dv dt. So to get an expression for a, we differentiate v with respect to t. So the derivative of 1 plus cos t is negative sine t. So we need to solve for t the equation acceleration a equals 0. In other words, negative sine t is equal to 0. And the solutions are t equals 0, pi, 2 pi, 3 pi, and so on. But like part 1, the value of t has to be greater than 0 and less than 3 pi. So the only valid solutions are t equals pi and t equals 2 pi. Therefore, the acceleration is equal to 0 at times t equals pi and t equals 2 pi. Part 3. Carefully sketch the graph of x equals t plus sine t for t greater than 0 and less than 3 pi. Clearly label any stationary points and any points of inflection. Recall that the position or the displacement x is equal to t plus sine t, the velocity v is equal to dx dt, which is equal to 1 plus cos t, and the acceleration a is equal to dv dt, which is equal to d squared x over dt squared. In other words, it's the second derivative of x with respect to t, and that's equal to negative sine t. Now, the possible points of inflection occur where a, or d squared x over dt squared, is equal to 0. So we're going to test the points where a is equal to 0. In other words, where t is equal to pi and t is equal to 2 pi, which we found in part 2. So I'm going to use a table of second derivatives and test for a change of concavity around t equals pi and t equals 2 pi. And the values that I've chosen are t equals 3, t equals 4, and t equals 7, around t equals pi and t equals 2 pi. So when t is equal to 3, the second derivative is equal to negative 0.1. And when t is equal to 4, the second derivative is equal to 0.8. So we have a negative second derivative here, a positive second derivative here. When t equals pi, the second derivative is 0. So we have a change of concavity around t equals pi, so that is a point of inflection. And testing around t equals 2 pi, so when t is equal to 4, the second derivative is 0.8, and when t is equal to 7, the second derivative is negative 0.7. So again, we have a change of sign in the second derivative, which means a change of concavity around t equals 2 pi. So we have a concavity change around t equals pi and t equals 2 pi, hence they are points of inflection. Also, the velocity v, or dx dt, is equal to 0 at time t equals pi, and this corresponds to a stationary point on the graph of x equals t plus sine t. Now, we previously saw that at time t equals pi, this corresponds to a point of inflection. So if it's a stationary point and a point of inflection, at t equals pi, this corresponds to a horizontal point of inflection on the graph of x equals t plus sine t. Now we need to find the vertical coordinates, or the values of x, that correspond to the values of t that we just found. And we also need to find the values of x that correspond to the endpoints of the graph. Recall that the interval that we're given is that t is greater than 0 and less than 3 pi. So using the equation x equals t plus sine t, at time t equals pi, x equals pi. At time t equals 2 pi, x is equal to 2 pi. At time t equals 0, x is equal to 0. And at time t equals 3 pi, x is equal to 3 pi. So here is a graph of x equals t plus sine t, as best as possible drawn to scale. So here are the endpoints, 0, 0, which is the origin, and 3 pi, 3 pi. Notice the circle there is not included in the graph, since t has to be less than 3 pi. It's not less than or equal to. Now I've labeled the graph x equals t plus sine t with the equation. That's important. And the question also asks us to label the stationary points and inflection points. So there's only one stationary point, which is at pi, pi, but it's also an inflection point. And there's also an inflection point at 2 pi, 2 pi. Now to get some extra points, I've done a table of values, which I haven't shown, just to get the curve a little bit smoother and a little bit more accurate. Question 9, Part A. A bag contains 2 red balls, 1 black ball and 1 white ball. Andrew selects 1 ball from the bag and keeps it hidden. He then selects a second ball, also keeping it hidden. Part 1. Draw a tree diagram to show all the possible outcomes. Note that this is a two-stage probability experiment involving selection without replacement, and that needs to be taken into account when determining the probabilities of each stage. Now, in the first stage, we have one black ball that we can choose from, one white ball that we can choose from, and two red balls that we can choose from. And that's why the denominators of the probabilities of the branches that make up the first stage are 4s. So after the first stage, one ball is taken out and hidden. That leaves 3 balls remaining, which is why the probabilities in the second stage all have denominators of 3. So here is the completed probability tree with the associated probabilities written on all the branches. Part 2. Find the probability that both the selected balls are red. Referring to the tree diagram that we drew in part 1, the probability that the first ball drawn is red is 2 over 4, and the probability that the second ball drawn is also red is 1 over 3. So the probability that both balls drawn is red, using the multiplication rule, is 2 over 4 times 1 over 3, which equals 2 over 12, which simplifies to 1 over 6. Part 3. Find the probability that at least one of the selected balls is red. By the law of complements, the probability that at least one ball drawn is red is equal to 1 minus the probability that no balls drawn are red. So referring to the tree diagram that we drew in part 1, there are two outcomes where no balls drawn are red. That is, this outcome here, we have black and a white, and this outcome here, we draw a white and then a black. So writing out the solution, the probability that at least one ball drawn is red is equal to 1 minus the probability that no balls drawn are red. And that's equal to 1 minus, open bracket, 1 over 4 times 1 over 3 plus 1 over 4 times 1 over 3 using the multiplication rule, close brackets, and that equals to 5 over 6. Part 4. Andrew drops one of the selected balls and we can see that it is red. What is the probability that the ball that is still hidden is also red? This is a case of conditional probability. We want the probability that both balls are red given that one of them has been revealed to be red. So using the results from parts 2 and 3, the probability that both balls are red is 1 over 6, and the result from part 3 is the probability that at least one of the balls is red, which we do know in this case here in part 4 that one of the balls has been revealed to be red, and that's 5 over 6. So using the results from parts 2 and 3, combining that together, the probability that both balls are red, given that one of them is red, is 1 over 6 divided by 5 over 6, which is equal to 1 over 5. Question 9, Part B. A pen moves along the x-axis, ruling a line. The diagram shows the graph of the velocity of the tip of the pen as a function of time. The velocity in centimeters per second is given by the equation v equals 4t cubed minus 24t squared plus 20t, where t is the time in seconds. When t equals 0, the tip of the pen is at x equals 3. That is, the tip is initially 3 centimeters to the right of the origin. Part 1. Find an expression for x, the position of the tip of the pen, as a function of time. To find an expression for the displacement or the position of the pen, which is represented by the variable x, we integrate the expression for the velocity v with respect to t. Now v is given as 4t cubed minus 24t squared plus 20t. So integrating this expression with respect to t, we get x equals t to the power of 4 minus 8t cubed plus 10t squared plus the constant of integration c, which we'll need to find using an initial condition or a boundary condition. Now it's given that when t is equal to 0, x is equal to 3. So substituting 0 for t here, here, and here, we get 3 is equal to 0 plus c, which means that c is equal to 3. So putting that all together, we get x is equal to t to the power of 4 minus 8t cubed plus 10t squared plus 3. Part 2. What feature would the graph of x as a function of t have at t equals 1? At time t equals 1, the velocity of the pen is equal to 0 because that's where the graph crosses the horizontal axis. And this implies that dx dt, which is the rate of change of the position of the pen with respect to time, is equal to 0. So this means there'll be a stationary point on the graph of y equals x of t at time t equals 1. Now, before time t equals 1, the velocity of the pen is positive because the graph is above the horizontal axis. And after time t equals 1, the velocity is negative because that part of the graph is below the horizontal axis. Therefore, the stationary point where t is equal to 1 will be a local maximum. Part 3. The pen uses 0.05 milligrams of ink per centimetre travelled. How much ink is used between t equals 0 and t equals 2? Since the pen changes direction at time t equals 1, to find the total distance, we integrate v with respect to t from t equals 0 to t equals 1, and then we add on to that the integral of v with respect to t from t equals 1 to t equals 2. And to ensure that both of these integrals result in a value that's greater than or equal to 0, in other words, ensuring that we don't get a negative value, we put absolute value brackets around each of these integral expressions. Now, if we're working out displacement, we won't need these absolute value brackets. But because we're working out total distance, whether the pen is moving forwards or backwards, it doesn't matter. So it's a bit like the odometer of a car. So it doesn't matter which direction the car travels, the odometer always moves forwards. Now we can use the expression for displacement from part 1. So since we've integrated v with respect to t already, the integral of v with respect to t is t to the power of 4 minus 8t cubed plus 10t squared plus 3. And we're evaluating this expression from t equals 0 to t equals 1. And we'll put absolute value brackets around that to ensure that it's a positive value or a non-negative value. And we're going to add on to that t to the power of 4 minus 8t cubed plus 10t squared plus 3 from t equals 1 to t equals 2. And we'll put absolute value brackets around that expression as well. So applying the limits of integration, we get the absolute value of 6 minus 3 plus the absolute value of negative 5 minus 6. Now the absolute value of 6 minus 3 is 3, and the absolute value of negative 5 minus 6 is positive 11. So 3 plus 11 gives us 14, and that represents the total distance travelled by the pen from t equals 0 to t equals 2. So to find the mass of ink used, the pen travels 14 centimetres and it uses 0.05 milligrams of ink per centimetre, and that gives us 0.7 milligrams of ink used. Question 10, Part A. Graph the solution of 4x less than or equal to 15 less than or equal to negative 9x on a number line. The strategy is to express this three-way linear inequality as an intersection of two simple linear inequalities involving two terms each. So breaking this three-way inequality up, noting that 15 is a common term to both simple linear inequalities, we form this expression. We have the intersection of 4x less than or equal to 15 and 15 less than or equal to negative 9x. Now we want the variable in the second linear inequality to be on the left-hand side of the inequality symbol. So if 15 is less than or equal to negative 9x, reading this backwards, that implies that negative 9x is greater than or equal to 15. Notice that the arrow points to the 15 in both of these inequalities. So we form this expression here. We have the intersection of 4x less than or equal to 15 and negative 9x greater than or equal to 15. Now isolating the variable in both simple linear inequalities. In the first linear inequality, we divide both sides of this inequality by 4. And in the second linear inequality, we divide both sides of this inequality by negative 9. And because we're dividing by a negative number, we need to switch the inequality symbol around. And we get the intersection of x less than or equal to 15 over 4 and x less than or equal to negative 15 over 9. And as mixed numerals, we get the intersection of x less than or equal to 3 3/4 and x less than or equal to negative 1 2/3. Now graphing the solution on a number line, we get this diagram here. So we have x less than or equal to 3 3/4. Notice the solid circle here and the arrow pointing to the left. And we have x less than or equal to negative 1 2/3. Again, with a solid circle with the arrow pointing to the left. Now it's a solid circle because it's less than or equal to, not just less than. On the diagram, the intersection of the two inequalities is where the two intervals that represent those inequalities coincide. And they coincide where x is less than or equal to negative 1 2/3. And that'll be our solution. Therefore, x is less than or equal to negative 1 2/3, because this value here satisfies both inequalities simultaneously. Question 10, Part B. In the diagram, Q is the point negative 1, 0, and R is the point 1, 0, and P is another point on the circle with center O and radius 1. Let angle POR equal alpha and angle PQR equal beta, and let tan beta equal M. Part 1. Explain why triangle OPQ is isosceles, and hence deduce that alpha equals 2 beta. In triangle OPQ, OQ is equal to OP because they are radii of the same circle, and that makes triangle OPQ isosceles. This also means the base angle of isosceles triangle OPQ are equal. So angle OQP, or angle PQO, which is equal to beta, is equal to angle OPQ, which is also equal to beta. Now this angle here, angle alpha, is the angle that is exterior to triangle OPQ. And the exterior angle of a triangle is equal to the sum of the opposite interior angles. So that's the sum of this angle here and this angle here. So they're both equal to beta, and that makes alpha equal to 2 beta. So looking at the proof, and it's written up here, OQ is equal to OP, since they are radii of the same circle, hence triangle OPQ is isosceles, and angle OPQ is equal to angle PQO, which is equal to beta, since base angles of the isosceles triangle OPQ are equal. Now angle POR is equal to angle OPQ plus angle PQO. And that's the exterior angle of triangle OPQ is equal to the sum of the opposite interior angles. So alpha is equal to beta plus beta. Therefore, alpha is equal to 2 beta as required. Part 2. Find the equation of the line PQ. Line PQ has a gradient of m, and the point Q with coordinates negative 1, 0 lies on PQ. And that's stated here. So line PQ has gradient m and point Q with coordinates negative 1, 0 lies on PQ. Hence, by the point gradient formula, y minus y1 is equal to m times x minus x1 in brackets, we have y minus 0 is equal to m times x minus negative 1 in brackets. Now x minus negative 1 is x plus 1, and y minus 0 is y. So y is equal to m times x plus 1 in brackets. Expanding the brackets, we get y is equal to mx plus m. Part 3. Show that the x-coordinates of p and q are solutions of the equation 1 plus m squared in brackets times x squared plus 2m squared x plus m squared minus 1 equals 0. The point P with coordinates x, y lies on the unit circle, which has equation x squared plus y squared equals 1. In other words, the coordinates of point P, when substituted into this equation, satisfies that equation. Now, line PQ with equation y equals mx plus m, which we found in part 2, is a chord on the unit circle. That means it contacts the unit circle in two places. Hence, the x-coordinates of P and Q are found by solving simultaneously the equations x squared plus y squared equals 1 and y equals mx plus m. So by substitution, in place of y in x squared plus y squared equals 1, I'm going to substitute mx plus m. So the equation becomes x squared plus mx plus m in brackets squared equals 1. Expanding using perfect square expansion, mx plus m in brackets to the power of 2, we get x squared plus m squared x squared plus 2m squared x plus m squared equals 1. Now notice in the first two terms we have a common factor of x squared, so factorising out x squared, we get 1 plus m squared in brackets times x squared plus 2m squared x plus m squared. Now taking this one here over to the left hand side, becomes minus 1, and that's equal to 0. Now this is the quadratic equation in x, whose solution gives the x-coordinates of P and Q. Part 4. Using this equation, find the coordinates of P in terms of m. Solving the equation from part 3 using the quadratic formula, and the equation from part 3 was 1 plus m squared in brackets times x squared plus 2m squared times x plus m squared minus 1 equals 0. So the values of a, b and c, where a is the coefficient of x squared, and that's 1 plus m squared, b is the coefficient of x, which is 2m squared, and c is the constant term, which is equal to m squared minus 1. We have x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So x equals negative 2m squared plus or minus the square root of 2m squared in brackets squared minus 4 times 1 plus m squared in brackets times m squared minus 1 in brackets all over 2 times 1 plus m squared in brackets. So expanding the brackets here using difference of two squares expansion, and also expanding the brackets here as well, we get x equals negative 2m squared plus or minus the square root of 4m to the power of 4 minus 4 times m to the power of 4 minus 1 in brackets all over 2 times 1 plus m squared in brackets. So expanding the brackets here, we get x equals negative 2m squared plus or minus the square root of 4m squared minus 4m squared plus 4 over 2 times 1 plus m squared in brackets. Now the 4m squared minus 4m squared cancels to 0, and we're left with the square root of 4. So x is equal to negative 2m squared plus or minus 2 all over 2 times 1 plus m squared in brackets. Dividing all terms by 2, we get x equals negative m squared plus or minus 1 all over 1 plus m squared. Now we know that the x-coordinate of P is positive. It's greater than 0. The other solution is the x-coordinate of point Q, which we know is negative 1. Hence x equals negative m squared plus 1 over 1 plus m squared, which is equal to 1 minus m squared over 1 plus m squared. Part 5. Hence deduce that tan 2 beta equals 2 tan beta over 1 minus tan squared beta. The point P lies on PQ, hence the y-coordinate of P is given by y equals mx plus m, which we found in part 2. So going back to the diagram, there's line PQ, it has equation y equals mx plus m, and point P lies on PQ. And we found the x-coordinate of point P, which was 1 minus m squared over 1 plus m squared. So when x is equal to 1 minus m squared over 1 plus m squared, substituting this value of x into this equation here, we get y is equal to m times 1 minus m squared over 1 plus m squared in brackets plus m. Factorising out m, we get y is equal to m times, open bracket, 1 minus m squared over 1 plus m squared in brackets plus 1, close bracket. Now combining these two terms inside the square brackets, finding a common denominator of 1 plus m squared, and 1 is 1 plus m squared over 1 plus m squared, we get y is equal to m times 1 minus m squared over 1 plus m squared plus 1 plus m squared over 1 plus m squared. Now we have a minus m squared here, a plus m squared here, so they will cancel to 0, and 1 plus 1 is 2. So inside the square brackets, we get 2 over 1 plus m squared, and then multiplying that by m, we get y is equal to 2m over 1 plus m squared. Now consider gradient OP. So going back to the diagram, O is the origin with coordinates 0, 0. We now have the coordinates of P in terms of m, and the gradient of OP is equal to tan of alpha. So going back to the diagram, that's our angle of inclination, and converting that into a gradient, that's tan alpha, and that's equal to rise divided by run. So 2m over 1 plus m squared divided by 1 minus m squared over 1 plus m squared, and that simplifies to 2m over 1 minus m squared. Now gradient PQ, which is equal to m, and that's equal to tan beta. So again, going back to the diagram, that's PQ, its gradient is m, and that's equivalent to tan beta, which is the angle of inclination of PQ. And alpha is equal to 2 beta, which we found earlier on. So substituting tan beta for m and 2 beta for alpha here, we get tan 2 beta is equal to 2 tan beta over 1 minus tan squared beta as required.